Hello guys, my name is Prasan and today is December 28th and I've started to work on this idea of sharing my LeetCode technique through the video. I have started doing LeetCode few years back. I used to first solve the problem and just leave it on the LeetCode. And then the second time what I started doing was I started pushing it in my own GitHub profile, and then the third time this like basically solving the same question. I already revised it for the two different times. Now third time started publishing the question in the blog in the form of blog in Unisala. And right now even the same question is this is my third fourth time looking at this question. And what I want to do is through this kind of video I want to share my techniques, how we can get better at data structure and solving LeetCode problem. So through this video, I'm going to share my techniques in solving this LeetCode problem. So this is the pattern. First minute, we will understand why is it we need to understand this question, like what is rotated sorted array, why we need to care, right? And then second minute we'll basically look at what is given from the question, what we can derive. And then third is we will basically use that knowledge to solve the question. So let's get into it. Here we are given an array which is basically rotated. I'll explain what rotated is, and we need to find the minimum from this array, right? And the constant is we need to find it in the log n time. Basically, if we don't have to find it in the log n time, we can just iterate over the array and then find the number we're looking for, right? In the log n, in the big O notation of n time. But we need to find it in log n time. And so let's understand what rotated array is. Let's say we are given this array where we have this kind of element 0 index, 1 index, 2 index, n minus 2, n minus 1. If the array is rotated twice, this means the last two elements comes out in the front, and that array is sorted right now in two different parts: the left sorted array and then the right sorted array. And similarly, we have this array we are given from example, and we have left sorted array and we have right sorted array. Every element in the left sorted array is greater than the element in the right sorted array, and so this is a sorted array. And from here, what we can conclude is, since we need to find something in log n time and our array is sorted, which is basically there is a, so then we can use a binary search, right? And what we have to find is, if we see a pattern here, uh, exactly at a point of pivotal, where this left sorted meets the right sorted array, that's where the minimum number lies, right? So we have to find this point, and let's see how we're going to find it. We now know we need to use binary search. We also know we need to find the pivotal point, and how are we going to find the pivotal point? If we just look at this two data, right? How are we going to find this pivotal point? If the data to the left of it is greater than this data, then we can know that this is a pivotal point. Okay, and so let's see how we can solve it. So we know we're going to use binary search, so we'll initialize how the basic wireframe for the binary search, which is L starts from 0 and the right starts from. What we need to do is basically we need to have L initialized to the first index and R initialized to the last index. So that's why n minus 1, nums length minus 1, and while. And so another thing is, do we need to have this like this or not? Basically, gonna have a scenario where both left and right index meet at a point. And do we need to care for those scenario or not? I don't think we need those scenario, because at this point we are just comparing two elements, right? We're comparing two elements and we'll be shifting our pointer based on those two elements. So we don't need to have a scenario where this left and right meets at the same position and then we'll calculate the index, mid index for the same position. No, we don't need that kind of scenario. So we'll just do where left is less than the right index, and we'll calculate the mid index. So mid index is max dot floor left plus right by 2, and we take the floor of, we divide. So for example, if we have a left plus right equals to 3, then we divide it by 2. We basically want 1. We don't want the ceiling. Basically, if it's 1.5, the base is floor is 1 and the ceiling is 2, we'll take the 1. So that's that. And now Here, what we know is all the small elements are in the right sorted part, right? So that means if mm, norms at left, basically, let's say at this point, this is where our left is. This is where our left is. Let's say this is our mid, right? And this is our right. At this point, if our left is less than this, then what we can understand is basically we are in the left sorted pipe. But if something, let's say we have this kind of situation, right, then we know that we are on the right sorted path. So from here we can, what we can conclude is, if less is less than mid, we are in the left sorted part. If less than is less than, if left pointer is less than the mid pointer, basically the data at left pointer is less than the mid pointer, we know that we are at the left sorted array, else we are at the anti right sorted array, right? And so now let's get into the meat part, right? So if we are on the left sorted array, what we know is basically all the small values on the right are on the right side. So if we are on this situation, we might want to move our left pointer to something like this, right? And then something like this, and maybe mid and right becomes somewhere similar, but anyway, something like this, right? We want to shift our whole focus to the right side. So that's where we do left moves to mid plus one. And we, if we are at the right sorted array, so for example, if the situation was like this, we have our left here, and we have our mid here, right? We have our right here, then we already know that we are in the right sorted part. So how are we gonna how are we gonna find the minimum? So the way to find the minimum is, we already know that we are in the right sorted part, and and the smallest value in the right sorted array lies in the leftmost of the right sorted array, or at the mean, or at the current mean, right? So the smallest value lies on the leftmost side of the right sorted array. So this is how we're going to do. So the right now becomes the mean, and then we are going to calculate for it. And so what? So this here, we are not returning anything here. So if we are at the left sorted array, we do this. If we are at the right sorted array, we do this. But if we find a pivotal point, that means, if we find a pivotal point means, so if at any point we find our pivotal point, mean if norms at mid plus one, which is this one, is less than the 5, then we also know that we found our pivotal point. So is less than norms at mid. So this is our mid. If the element at mid plus 1 is less than mid, we know that this is a pivotal point, and we can just return this minimum, which is norms at mid plus 1. And so this is our answer. But so by that, okay, if we find it, we'll return it. But if the loop closes and we have to return the minimum element, what we are going to do is, by this time we have done the computation, and our algorithm resolves the left and right to a point where our minimum will be given by norms at left. Basically, you want to check from left and right, and then as you do the comparison, you find the minimum, and you adjust the pointer depending on where you want to go. Okay, and then one thing you need to do is, if the array is already sorted, right? If this is the case, if the array is already sorted, then you will have a default value where the left pointer is always less than the right pointer. Uh, So less than right, lower, and then norms as mid plus and norms return norms. Oh, I have to return this. Sorry. And then here, I don't write this inside this, I only write this outside the file. Okay. it's 100% of the runtime. Okay, so now this is the solution, and this looks really nice. Let's also discuss the complexity, right? Uh, it's straightforward, I guess. This time we are using the binary search, which means we have log n, and we are not initializing any array, so it means our complexity, space complexity of O of n, and time complexity of log n. So it looks very nice. So that's this. I'll see you guys in the other video.